Hey everyone, welcome back to the Math Corner. Today, we'll be covering 1.5, Part 1, Exponential Functions. Let's get started. So, what are exponential functions? Exponential functions are functions with the form f of x equals a times b to the x. So, what do you notice about this form? We see that x or that b is being raised to an x power. Normally we've seen x being raised to a constant number's power, right? Like in polynomials. But in this case, we're seeing a constant such as b being raised to the x power. So b is our multiplier, and obviously a is our starting value. When x equals 0, b to 0 is just 1, so a would just be our y-intercept. What's the point of all these exponential functions? Why should we overcomplicate these things? Exponential functions are good for modeling growth and decay. So for example, if I deposit $1,000 into a bank, that gives me 10% returns every year. That gives me 10% returns every year. That means at the end of the year, I would have $1,100. So I guess I could keep doing that again and again, but it would be so much easier if we could just come up with an equation. So how would I do this using exponential functions? Well, I can use the function f of x, which could model the total amount of money that I have in the bank account. I'll set that to our initial amount, our starting amount, multiplied by 1.1, which is basically 10% more, raised to the x power, where x is the number of years. So every year, whatever my previous year's amount is gets multiplied by 1.1. So at year 0, I have 1,000. At year 1, I have 1,100. At year 2, I'll have $1,210, so $1,210, and so on and so forth. That's one example of how exponential functions can be used to model growth and decay. Okay, so let's talk about graphing exponential functions. Exponential functions are functions with the forms f(x) equals a times b to the x, and a and b have to be both positive. So there are two types of exponential functions. I mentioned before they were exponential growth and exponential decay. Exponential growth is when the function has a value b, which is our multiplier, that is greater than 1. It's not greater than or equal to 1, it's greater than 1. So these functions, as you go like closer and closer to negative infinity, these functions approach 0. And when you go and you travel in the positive direction, you will see that these functions, they increase rapidly. Exponential decay, on the other hand, is when b is, obviously greater than 0, but is less than 1. Not less than or equal to 1, just less than 1. These functions start out at really high values, but then they gradually approach 0. So this is if b is greater than 0 but less than 1. So the blue one is exponential growth and the pink one is exponential decay. Okay, so let's quickly go over some exponent properties, okay? So if you have a to the x times a to the y, that's equal to a to the x plus y. If you have a to the x divided by a to the y, that's equal to a to the x minus minus y. A to the x divided by a to the y is equal to a to the x minus y. If we have a to the xy, that's equal to a to the x to the y power, and or a to the y to the x power. If you have a to the x times b to the x, that's equal to ab to the x power. You can almost factor out the x from a and b. And a to the x divided by b to the x equals a divided by b to the x power. So those are just some exponent property. They're a good idea to memorize them. Okay, so the last concept I'd like to cover is Euler's number. What's so special about Euler's number, though? Euler's number is a number that's very special in calculus. It's not that obvious right now, but later, as we cover more chapters, as we learn more calculus, it'll become more obvious. Euler's number is what you get when you plug in increasingly large values of x into this function. 1 plus 1 over x raised to the x power. As you plug in larger and larger values of x, f of x is going to get closer and closer to Euler's number. It's basically a horizontal asymptote at y equals e. E is Euler's number. So this is kind of like a sneak peek into our next unit, limits. So how would you notate this using limits? You would say the limit as x approaches infinity. So as we start using values of x closer and closer to infinity, so basically larger and larger values of x, as x approaches infinity, the limit as x approaches infinity of 1 plus 1 over x raised to the x power equals e. And in the table below, you can see that as x gets greater and greater and greater, f of x begins to approach a certain value around 2.7. And that's Euler's number. So Euler's number is equal to E, which that's how you notate E. And that's equal to 2.71828. You're not expected to memorize this. But yeah, this is what Euler's number is. This is what you get as you plug in larger and larger values of x into this function. So yeah, that's just Euler's number.